Section 2.5 is titled Complex Zeros and the Fundamental Theorem of Algebra. What we're basically doing in this section is expanding on what we did in the last section. In the last section we were talking about finding rational zeros and then expanding that to real zeros with the last example. And in this one we're expanding that to complex zeros. Okay, zeros that are maybe non-real, so imaginary zeros. First thing is the Fundamental Theorem of Algebra, and it says this. A polynomial function of degree n will have n complex zeros. Complex zeros are, of course, real and non-real zeros. Okay. I'll also add this. Some of these zeros may be repeated. Okay, so it's not in a polynomial function of degree n, and we'll have n distinct complex zeros, distinct meaning different. Some of the zeros may be the same zero. Think of the multiplicity of a zero we've talked about, the graph that bounces off the axis and doesn't go through it. So that can happen as well. But that's what we're guaranteed, that if we have, no matter what the degree of the function is, that's how many zeros we're going to have. So we basically, when we're asked to find the zeros of a function, you can't end your search for zeros until you have as many as the degree of the function. Simple as that. Now, one thing about this theorem real quick, it's what we call in mathematics an existence theorem. It tells you that these zeros exist, but it doesn't tell you how to find them. Okay? So the how to find them are some of the tools and strategies, resources that we've been using so far in this chapter up to this point. But again, it tells you that they're there, and then we got to go about finding them. One other theorem that I'd like to write out before we start looking at problems is the complex zeros theorem. And it says that if a plus bi is a zero of f of x, polynomial function f of x, then a minus bi is also a zero. In other words, complex zeros of polynomial functions, they always come in plus minus pairs. Okay? They always come in plus minus pairs. These are called conjugate pairs. Okay. So that's important. If you have an imaginary zero or a complex zero, if you're given one of them, this theorem guarantees the other one is also a zero. And that'll be important to us. We're going to begin the problems with some examples of writing polynomial functions in standard form with given zeros. And we did this at the end of section 2.3. So we're going to just kind of revisit it here. This time we're looking at some that have complex zeros. Okay, so we begin with a function. I'm going to write this function in a factored form. If positive 4 is a zero, then x minus 4 was the factor. If positive 3i is a zero, then x minus 3i is also a factor. Now, according to that complex zeros theorem, if this one is a zero, then so is negative 3i. Because again, they have to come in positive, negative pairs. So that means we would also have x plus 3i. And now to get it into standard form, we're just going to do a lot of foiling, or repeated foiling. Okay. Now I'm going to begin with these two. Always do the plus minus pairs first, the conjugate paired complex zero factors first. Okay, it's going to create opportunities to cancel very nicely. So we'd have x squared plus 3ix minus 3ix minus 9i squared. We need to do a little bit of simplifying there. These cancel. That is not supposed to be x squared. That was supposed to be I squared. Got a little mixed up on my variable. So this is x squared plus 9. Okay, remember that I squared is equal to -1. So I just substituted that, became plus 9 here. And now we can continue by doing one more FOILs process. It's x to the third minus 4x squared plus 9x minus 36. There's our f of x function. Okay, same directions on this one. We're asked to do the same thing, write a polynomial function of minimum degree in standard form whose zeros include -1, 2, 2 minus I, that's a binomial, 2 minus I, which means that 2 plus I is also a 0. It's not given, but we need to know it from that complex zeros theorem. So I'm going to begin by writing out all the factors. -1 is an x plus 1. +2 is an x minus 2. 2 minus I is an x minus 2 plus I. And then 2 plus I is an x minus 2 minus I. Again, I'm getting these because it's just opposite sign. Okay, just like these simpler ones where it's opposite sign or opposite signs, both. Okay, make sure we're distributing that. Okay, so I'm going to multiply these together. That's x squared minus x minus 2. And I'm also going to multiply these together. And this is going to take a little more work because it's a trinomial by a trinomial, and there's going to be lots of canceling. So let's do that and see what we get. I'm going to do x to all three of these first, which is x squared minus 2x minus ix. Now I'm going to do -2 to all three of these. Minus 2x plus 4 plus 2i. And I'm going to do I to all three of these. It's plus ix minus 2i minus I squared. Okay, all the i's need to go away. If I did this right, all the i's will cancel. -ix, positive ix are gone. Positive 2i, negative 2i are gone. Negative I squared, same as positive 1. Okay, I'm going to put all those like terms together. It's x squared minus 4x plus 5. Okay, and I had this x squared minus x minus 2. Okay, now we're going to do it again. We need to multiply, continue to multiply these together to end at the result. So we've got, I'm going to do x squared times all three, then the middle term times all, and -2 times all. So this is x to the fourth minus 4x to the third plus 5x squared minus x to the third plus 4x squared minus 5x minus 2x squared plus 8x minus 10. Like terms, find them. Okay, so there. I've tried to identify them with some different looking squiggles. So the f of x is equal to x to the fourth minus 5x to the third plus 7x squared. Looks like plus 3x minus 10. And done. Alright, one more example with a different sort of look to it. Write a polynomial function of minimum degree in standard form whose zeros include. So here we don't see any complex zeros, but we see this multiplicity. That's what that means. Multiplicity of 3, multiplicity of 1. So negative 1 is a 0. That means x plus 1 is a factor, but multiplicity of 3 means it's x plus 1 cubed. And then we have positive 3, which is an x minus 3. X plus 1 cubed is x plus 1, x plus 1, x plus 1, and then the x minus 3. So if you were going to FOIL this, you'd have to just do 2 at a time. You could do these 2 and these 2 and then take their respective answers together. I'm going to speed it up. If you remember for this right here, if you remember Pascal's triangle, you could speed this up. If I remember to do it, I'll link the video that shows Pascal's triangle. It would be an Algebra 2 video, but I'll link that and you can go back and look at it if you want. But x plus 1 cubed is x to the third plus 3x squared plus 3x plus 1. X minus 3 is still there. So if you knew Pascal's triangle, you could do that as fast as I did without having to multiply all these together. And now I'm going to take all this times x minus 3. So I'm going to do this one to these two, and then this one to these two, etc. on in. So it's x to the fourth minus 3x to the third plus 3x to the third minus 9x squared plus 3x squared minus 9x plus x minus 3. Okay, so like terms, it looks like that one cancels that one. I don't think anything else just outright cancels. So we have x to the fourth plus, I'm going to say 3x squared. No. Let's try that again. X to the fourth minus 6x squared minus 8x minus 3. There's our polynomial function. And if I hadn't scribbled that out, I'd write f of x equals in front of it.